Yes, I can see. So yeah, it's a lengthy title, so I tried to guide you through this many different concepts which combine together and understanding how models represent these features of atmospheric circulation and related extremes, and also how is it projected in the future. First of all, I would like to say thank you very much for inviting me, and I'm so excited to present this work to you. And also, I would like to say thank you very much to my collaborators helping me to finalize this work. I will talk about importance of heat waves in our studies, and as we already saw, as the presenters showed to us, that in the future with global temperature increase, we're going to have more drastic conditions. We need to be able to prepare for them, and therefore it's quite important to study heat waves. From Java point of view, Rossby waves are found to be connected or causing Eurasian heat waves. And I have here quite an illustration showing that these Rossby waves are sort of indulation in atmospheric fields in tropospheric circulation. And usually we present them as high and low spanning all over the globe, particularly in mid-latitudes. So what about blocking, you would ask? And the thing with stationary Rossby waves, that when they moving or stationarize, then there are persistent circulation, which is characterized by potential height anomalies over high hectopascal as a reach, as you can see here as an example. What's happening for us on surface, that this drives warm air from southern region and therefore amplifying surface. And from vertical perspective point of view, this high pressing down the air, which warms up and further heats the surface. Problem with this blocking that it persists for several days, and therefore that reinforces the process, and then the heat, the hotter days we get in the end. What about future? Unsurprisingly, future heat waves will increase in duration, magnitude, frequency with respect to present-day climate, as I said, as a consequence of projected mean temperature increase due to greenhouse emissions. However, future changes in atmospheric circulation that associated with heat waves much less certain. For example, the latest IPC report shows medium confidence in increase of amplitudes of these stationary waves. Furthermore, projections of blocking differ among metrics and region. What I want to highlight here, that we will discuss this connection further on, and we assume that according to other studies that the link is realistic. Therefore, by keeping this link, we can better understand projected circulation changes while we know what's going to happen with heat waves in the future. What I want to show here, that the study working on particle variability in planetary-scale Rossby waves will help us to understand uncertainties a bit better. And therefore, I'm focused on these three questions. And first one, it's introduction to the model assessment, when we used reanalysis to identify signatures of Eurasian heat waves in global Rossby wave spectra. And you feel free to get more details in the paper where I discuss other parts. In the interest of time, I'll focus only on planetary scale. But main body of the presentation today is model assessment. And first, I will discuss how CMIP model represents statistics of Rossby waves and how it's going to change in future. And this work is under revision, and you can find it on each year's fair. A bit of what data we used, and for the first part, or what we call reanalysis study or reanalysis, we used 4 analyses with main focus in year 5 as considered to be state of the art. For models, we used only subset of models due to availability of the data, and then later on I will explain why. We also use different horizontal resolution, as you can see here on the table, but then we regraded them for circulation analysis further on. There is also a different number of vertical levels and truncation, but therefore we want to see how these parameters actually presented in models with respect to reanalysis. What I want to also highlight that we used several simulation runs. We used typical present-day climate historical simulation. We also used CMIP, atmosphere only, and we used middle road RCP 4.5 analysis. Speaking about the tool, what we used for this one, advantage that we can decompose several fields that combine together into series of two-dimensional oscillations in with various vertical structure. These tools also allow to separate Rossby contribution and non-Rossby contribution, which is important for different set of topics, which I'm not covering now, but you're free to read about this a bit more in Jagar et al. In 2015. There's a illustration of how usually it's done. We have, for example, wind field, which we combine with the potential height fields, which then represented as half harmonics with related half coefficients, which are three-dimensional. Again, in the interest of time, I'm focusing only on zonal wave numbers, and we select planetary scale as zonal wave numbers from 1 to 3. The reason why we have subset of models is relatively short, because this tool requires different model levels and different parameters, and therefore that limits our selection of models. But then let's go to results. First, I would like to show only year 5 as example, because other analyses show similar features. And these two, what I described in the previous slide, allow us to take part of circulation and then project it back to physical space. Therefore, we can analyze features of only chunk of circulation, which is quite advantageous. Like, for example, this Eurasian heat waves composites is clearly show high over Western Europe and Scandinavia, meaning that indeed in this planetary scale there's big part of circulation which is responsible for heat wave extremes. But now we are more interested in going in a bit more details, and this tool allows us to perform statistical analysis in spectral, or we call a model space. And basically, this slide shows how we can obtain this probability density function during heat waves. We start with average temperature time series. Then we identify in classical way more than 3 consequent days, and these events are basically some sample to create PDFs during heat waves. What it gives us, we found that for planetary Rossby waves, there is increase in skewness, which is characterized by increase in probabilities of upper tails, distribution of energy anomalies, which are found to be statistically significant, as you can see on the right. Small note about energy here, that this is similar to total energy, which is a sum of kinetic and potential available energy, which can be transferred to physical space to be more comparable with other studies. I also would like to make a note that due to relatively small sample size for each analysis, we combine several of them together. Okay, now my focus is on model circulation or models, how they perform special patterns. And what we see here, this is our era 5 during heat waves and several of models with different historical and EMI prompts. Overall visual inspection says that in all these models, we see increase in the potential height, and it's correctly shows location, but atmosphere-only circulation shows a bit better intensity resemblance with ERA 5. However, if you look at projections of this circulation, we see that not every model agrees with one another. For example, GFDL models show decrease in the potential height during future heat waves, while for other two models, we see an increase. Therefore, there is a clear discrepancies. To answer the question why we observe this, we can come back again to analyze these PDFs in spectral space and see how models actually can capture this increase in skewness. Unfortunately, we found that none of these simulation represent this increase in upper tails, and in even some of them, for example, atmosphere only and feature projection show decrease in skewness. So then it's create a puzzle why even in physical space we observe these features, which is completely different spectral space. And one hint to this is that if you look at changes in skewness in particular model and in particular run, we found absolutely different results, completely one showing. That indicates that there is a lack of robustness of among models and between reanalysis and models. Therefore, I would like to move to summary and just recall a bit what I was talking about. To answer this first question, we found signature of Eurasian heat waves as increase in amplitudes of planetary waves and also in skewness of PDFs in spectral space. We found that models can represent special pattern of planetary scale tropospheric Rossby waves, but we didn't find good agreement in change of day-to-day variability among models and between models and reanalysis. Regarding the future changes, we found that models indeed project surface warming, but they differ in prediction and associated Rossby waves. Particularly, we found very little confidence in how day-to-day variability is going to change, and we associated with the fact that present-day simulations already have large deficits with respect to this parameter. And I would like to spend a couple of more time talking about what actually it means for CMIP community. We know that uncertainties in atmospheric circulation and associated variability limits confidence in heat wave projections. What I found in my study that changes in day-to-day variability possibly suggest shifts in internal dynamics, and something I haven't discussed, something which requires additional analysis, is the role of wave and wave mean flow interaction. What I would like to highlight in my presentation that in most of assessments, we look at averages, which can mask inconsistencies and errors. If we incorporate in our evaluations more of variability metrics, we probably can improve reliability of future projection and, of course, representation of present-day climatology. And here's my last slide. This is the screenshots of these two papers I was talking about. You're welcome to look a bit more and contact me either via LinkedIn or as an email. Thank you for attention, and now I am open to the questions.
Thank you, Iana. We've got a bit of time left for some questions. I don't see any hands up. Has anybody got a question they want to ask? I've got one question. I suppose this was a study based on previous iterations of CMIP. Do you foresee that with CMIP 7, for example, these discrepancies will improve, or is that something you're going to look into?
That would be an excellent study, I would say. I mean, we had a bit of discussion regarding CMIP 6, and we did a bit extra step in, at least in temperature representation, how it changed and related heat wave extremes. But we didn't find robust feature in atmospheric circulation, and indeed, several studies show that improvements from CMIP 6 from CMIP 5, it's not that, let's say, promising. Of course, there are improvements in frequency, but then there is question with duration, and not every region improved at the same extent as others. So I hope we have a bit better picture, and indeed, maybe some parts will be better represented, because unsurprisingly, most of problems stem from, for example, parameterizations. But as I show in my presentation, we have problems with bigger issues, for example, wave and wave interaction, and so now mean flow interaction. And if we have this issue in CMIP 6 and we don't think how we can improve it in CMIP 7, when we basically get the same results as I discussed today.